All right, so today I'm going to tell you about some joint work with Jenna Ratchgott and Anna Wygant, in which we are studying these Kazhdan-Lusztig varieties and are using the combinatorics that we have at our disposal via Grothendieck polynomials to compute a particular invariant called Castelnuovo-Mumford regularity. And to start with, we'll pick back up with our Schubert varieties, which everyone should be familiar with at this point. To build our Kazhdan-Lusztig varieties, I'll give one disclaimer that my conventions are different than Laura's. Small disclaimer, but I'm going to give all of the background again, so hopefully this won't cause any issues. All right, so we start with our Schubert varieties, and we can again act on our Schubert variety by the maximal torus, so those diagonal invertible matrices. And we know that every point on our Schubert variety is going to be in the Borel orbit of one of these torus fixed points. Moreover, this action of the Borel is going to give us an isomorphism between local neighborhoods around any of these torus fixed points and any point on our Schubert variety. So if we're asking local questions about our Schubert varieties, then we might as well just focus on these local neighborhoods of these torus fixed points. And this was the strategy used by Wu Yang in 2006, in which they were interested in classifying certain singularities of these Schubert varieties in terms of interval pattern avoidance. And so what they did is they said, well, let's look at this lemma from Kazhdan-Lusztig, which says that if we're looking at these local neighborhoods of torus fixed points on our Schubert varieties, which is this left-hand side, that's going to be the same as taking an intersection of our Schubert variety with an opposite Schubert cell, and then we'll have a factor of affine space hanging off the end. And by throwing away that affine space and focusing on what's left, that gives us this Kazhdan-Lusztig variety. And again, as was mentioned in Laura's talk, we have really clearly defined equations that are cutting out this variety, as given by Wu Yang. Although I think this is in their 2012 paper, not the 2006 one. And so I'm just going to go over this defining ideal again, just so we're all clear with the definition of these varieties. Okay, so what we'll do is these varieties, in terms of their definitions, we know that this permutation W is always going to be less than or equal to V in Bruchau order because these varieties are coming from these torus fixed points. And so what we'll do is we define these ideals in terms of this pair of permutations V and W, where again, W is going to come into play by telling us what rank of minors we're going to take to build our generators, and this big permutation V is going to tell us what matrix we're going to take these minors of. So here I have, let's see, the pointer isn't working, but that's okay. So here I have W is 4, 1, 3, 2. And so on the left-hand side, I've drawn the Rotha diagram for the permutation 4, 1, 3, 2 in my convention. So this is row-centric convention, which means that since W is 4, 1, 3, 2 in one-line notation, I'm going to put in the first row, column 4. Since 1 gets sent to 4, I'll put my bullet there. And I follow those conventions throughout to draw my diagram. Okay, so for example, from the Rotha diagram, it's easy to read off the rank matrix of the permutation W, because you can just sit at whatever position in that Rotha diagram according to which position you want to calculate the rank matrix of, and just ask how many of these bullets in my Rotha diagram do I see looking northwest of that position. So here I see 2 bullets, so I record an entry of 2 here. All right, so we have our rank matrix, and then to build the matrix we're taking these minors of, which is determined by this big permutation V, the one that's our torus fixed point. We are essentially going to, again, redraw the Rotha diagram, except instead of recording boxes, we'll record those positions with indeterminate Zij's. Instead of bullets, we'll draw 1s. And instead of our death rays, we'll have 0s. And so what this definition is saying is I'll pick a corner, a lower right-hand corner for my matrix, my submatrix to take minors of. And the size of minors I take is going to be determined by the corresponding entry in the rank matrix of W plus 1. So if I'm taking the submatrix determined by this lower right-hand corner here, this red submatrix, the rank matrix of W tells me I'd take all of the 2 minors of this red submatrix, which is going to give me these generators here. Or I could take this lower right-hand corner to give me this blue submatrix, and the rank matrix of W would tell me I'm going to take the 1 minors of this blue submatrix, which is going to give me these 3 generators. And so a theorem of Fulton, which carries over to this Kazhdan-Lusztig case, is it suffices to only take these submatrices, so choosing these lower right-hand corners, based on the essential set of our diagram. Those are going to give us our essential generators. All right, so as it turns out, because of this theorem, these are all of the generators that we need to write down to generate this defining ideal. So you can see in this definition, you could cook up an example in which these generators are no longer homogeneous, which could be problematic. But in all of the cases we're going to talk about today, everything will be homogeneous and will always be using the standard grading. So everything will be nice and easy for the things that we'll be talking about. But there certainly are more interesting examples where you might need to use a multi-grading. All right. Further, special cases of these Kazhdan-Lusztig varieties are our matrix Schubert varieties that we've seen throughout the past week or so, which you can realize by taking the permutation V, sort of taking it really large so that you have a big rectangle of these indeterminates, and you can recover the matrix Schubert varieties that way. Similarly, you can cook up a classical determinantal variety, which are just taking, for example, all L minors of a rectangular matrix, because those are special examples of matrix Schubert varieties. So they're again going to be special cases of these Kazhdan-Lusztig varieties. Right. So in closing, these Kazhdan-Lusztig varieties just give us many, many nice different determinantal varieties, generalized determinantal varieties. And so we'll be able to see them popping up in a lot of different settings where they're unified by this Kazhdan-Lusztig umbrella. One thing that we can study about these varieties is because they come from this nice geometry, they're Cohen-Macaulay. And so their commutative algebra is going to be more well-behaved. So for example, we can compute its minimal free resolution. So we can start with its coordinate ring here, where I'm drawing with S mod I, and writing out its minimal free resolution that Jianping was talking about on Monday. So we can resolve with these free S modules, where you're shifting in degree, where the multiplicities of these free S modules are these multigraded Betti numbers, these beta ij's. And so when you're studying these coordinate rings, one statistic that you can pull out is the K polynomial of that coordinate ring, which you can realize as the numerator of the Hilbert series, where the Hilbert series is a generating series whose coefficients are recording the dimension of each ith graded piece. So these coefficients are determined by the Hilbert function. Okay. And a different way that you can write down the K polynomial, maybe you don't want to write down the Hilbert series and all of that data. You can also read off this K polynomial using these multigraded Betti numbers by taking an alternating sum. Again, from these multigraded Betti numbers, you can read off the Castelnuovo-Mumford regularity. So one way that you can sort of interpret it is this sort of thickness of the minimal free resolution that Jianping was talking about. And more explicitly, this is just coming from us reading off what is the maximal difference between indices that we can have in the Betti numbers that actually appear. So among these non-vanishing Betti numbers, what is the maximal difference in those indices? Some reasons that we might want to compute this regularity is it gives us a bound for when the Hilbert function and the Hilbert polynomial will exactly coincide. So we know the Hilbert function is approximated by the Hilbert polynomial, and when we're plugging in large values, so when we're looking at the dimension of graded pieces where we're plugging in n large, we know that the Hilbert function and the Hilbert polynomial will coincide. But this regularity tells us a bound for when we know that we can actually, instead of worrying about computing in terms of the Hilbert function, we can use this Hilbert polynomial to get these computations, which is significantly easier. So practically, we might want to be able to easily compute this regularity. Additionally, it just gives you a rough bound for sort of how complicated your minimal free resolution is. But if I'm trying to figure out how complicated my minimal free resolution is, I don't want to have to compute the minimal free resolution to be able to compute the regularity. I don't want to have to compute these Betty numbers to get a hold of this regularity, because that's hard. So what we'll do instead is recognize the fact that our coordinate ring is well behaved. It's Cohen-Macaulay. And so as it turns out, we can instead compute this regularity in terms of the K polynomial. Specifically, what we can do is read off the degree of this K polynomial and subtract off the codimension of the ideal. And when we're in the Cohen-Macaulay setting, that will give us precisely this regularity. And you might ask, well, do we not need this Betty number data to compute these K polynomials? And in general, you might need this, but in many settings, we have some combinatorial interpretation for these K polynomials that might make these computations a bit nicer. And luckily, in this Kazhdan-Lusztig setting, that's precisely what we have. An even nicer setting than the Kazhdan-Lusztig setting is this special case of matrix Schubert varieties. So we know that those are special cases of these Kazhdan-Lusztig varieties. And so again, these matrix Schubert varieties are Cohen-Macaulay, so we can apply this theorem to those. And what this theorem says in that case is the regularity of these matrix Schubert varieties is going to be computed by taking the degree of its K polynomial and subtracting off the codimension of that defining ideal. In Fulton's paper, in which he introduces these matrix Schubert varieties, he already identifies the codimension of these defining ideals as being the Coxeter length of the permutation. So that's just the number of inversions in the permutation. So that's extremely easy to compute, which is great news. So now we have to think about what is this K polynomial, which you can identify through work of Buch and Knudsen-Miller. So we know that the K polynomial of the matrix Schubert variety is the Grothendieck polynomial, which we've seen mentioned a little bit throughout, but we'll get to a definition shortly. So what this tells us is if we are able to compute the degree of this Grothendieck polynomial, then we'll just throw away the trash of the Coxeter length, and we'll have this regularity computation. So I think this appears in the quiver varieties paper. You can talk about this later. But thank you. Okay, so now let's try to get towards some easily computable formulas for the Grothendieck polynomial. All right. And before we get to the Grothendieck polynomial, this inhomogeneous setting, let's think about maybe a simpler polynomial, our most familiar Schubert polynomials. And so we can use Bajorard-Billy's formula in terms of pipe dreams as one particular formula that we can compute a generating series for these Schubert polynomials in terms of these pipe dreams, which I believe you've seen last week. So here I have the pipe dreams for this particular permutation W, and you might say, you know, there's no pipes here. That's not a pipe dream. But I was just lazy and didn't write the sort of elbow tiles because once you know where the crosses are in your pipe dream, everything else is implied. So here I have all of the reduced pipe dreams from my permutation W. And so we know we get these pipe dreams by starting with our initial configuration of pluses here, this bottom pipe dream, and we apply all of these ladder moves here, where in this case, we're not having here k equals 0. We're just doing these most simple ladder moves where we're not hopping over any stacks of pluses for these moves. And then we record monomials according to each of these pipe dreams by multiplying xi to the number of pluses in row I. So here this pipe dream gives us an x2, and this pipe dream gives us an x1. All right. So that's our Schubert polynomial. And it's apparent from this definition that the degree of at least the Schubert polynomial is easy. It's just the Coxeter length. And one way that you can see this really concretely is the number of pluses that you start out with is the same as the number of boxes in your Rotha diagram, which is just the Coxeter length. Okay, so at least the Schubert problem, this Schubert problem is easy. Okay, so what about the Grothendieck version? Luckily, we can slightly adapt this rule and get a rule that tells us how to combinatorially compute the Grothendieck polynomial. So we saw, I think on Monday, we can compute these Grothendieck polynomials using isobaric divided difference operators, but that doesn't give us as much combinatorial intuition. But we have a very similar rule in terms of pipe dreams. And so for this, it's going to be rather similar. So we'll start with our same initial configuration of pluses, and then we're going to do k ladder moves. And so I'll be able to do these two moves, but I'm just going to add one more move that I'll be allowed to do. So I could do my ordinary ladder move, or I could sort of leave a copy of the plus behind as I'm hopping over this stack of pluses. Okay? And so by doing this more k-theoretic ladder move, this is going to strictly increase the number of pluses by 1 with every time that you're doing one of these moves. Okay, so in this example, this is my starting configuration. I can do an ordinary ladder move, or I could do a k-theoretic ladder move here. And this is giving me all of the possible pipe dreams in this case for these k-theoretic pipe dreams. In the same way that we did before, we can record monomials for each of these pipe dreams. And we'll just introduce this sign that's going to alternate in every homogeneous degree component. And so what would the degree be in this case? So it's inherent in this definition, sort of this thing that Jianping was mentioning, is that the lowest degree terms in your Grothendieck polynomial are going to be exactly your Schubert polynomial. And that's clear just from this definition, because if I'm not doing any k-theoretic moves, I'm going to get all of the monomials that I got in the Schubert case. Okay, so then we see that the degree of the Grothendieck polynomial is going to be what is the most number of pluses that I can possibly create in doing these moves. And that tells us that since these Grothendieck polynomials are the k polynomials of the matrix Schubert variety, and the degree of the Schubert polynomial is exactly that Coxeter length, which was the codimension of the defining ideal for the matrix Schubert variety, the regularity for this matrix Schubert variety is going to be what is the difference in degrees between these two polynomials. So what we really need to measure is what is the most number of these k-theoretic moves that we could possibly do. And you might say, let's just do a greedy algorithm and try to stuff as many pluses, as many of these k-theoretic moves as possible. But it's hard to know which ones you should be doing. So a greedy algorithm really doesn't work in this setting, and so you have to be a bit more clever about it. And so myself, with Jenna and Anna, were interested in studying this problem. Initially, along with Avery and Yiren, we solved the Grassmannian case using a theorem of Leonard. And so we said, with Jenna and Anna, we said, let's try the vexillary case. And so we were able to, using some extra combinatorial structure that's given to us in this vexillary setting, we were able to get a combinatorial formula for the degrees of these vexillary Grothendieck polynomials, where the vexillary Grothendieck polynomials are those that are indexed by 2, 1, 4, 3, avoiding permutation. Okay. And so what this rule says is I'm going to start with my Rotha diagram, which should be very familiar to all of us. And I'm just going to store the entries of the rank matrix in the boxes of the Rotha diagram. And then I will just move these boxes northwest along diagonals to create a tableau. Fine. And then I'm going to just read off this regularity statistic, or this degree statistic, by looking at anti-diagonals inside of this tableau. So I'll have a contribution from the Coxeter length, which is the number of boxes here, which is 12. And then we have a short algorithm to compute the rest of these contributions. And that algorithm says we'll start with I equals 1, by restricting to all of the entries of this tableau that have labels at least 1, what is the longest anti-diagonal of boxes with entries at least 1? And so here I have these two boxes and this box. So I have an anti-diagonal of length 3 that has entries at least 1, which is giving me this 2 plus 1 contribution. And then for the I equals 2 step, I look at anti-diagonals in the subtableau that has entry at least 2. And that's just this one box here, which gives me this plus 1. And if I try to do this for other higher index steps, that's not going to give me any contribution. And so I'll be done. And so we get that the degree of this particular growth unique polynomial is 16. We have a similar formula for 1432 avoiding permutations. But luckily, Pechenik-Spire-Wigand have a formula for any permutation that you can want, okay? Which Jianping mentioned is in terms of you look at the word, just the permutation in one-line notation, and reading off these sequences, you can exactly read off not only the degree of this growth unique polynomial, but you can actually find what monomial, a monomial that actually is contributing to that. And then, of course, as we saw on Monday, we have a way to, just in terms of the diagram as well, using these node diagrams of Tianyi Yu and Jianping Pan, actually getting another formula for the degree of these growth unique polynomials in general. So we have lots of great ways to compute these degrees of growth unique polynomials. Okay. So we have the formula in this vexillary setting. We have formulas in all of the matrix Schubert variety settings. So now let's maybe go back to the Kazhdan-Lusztig setting and see what we can talk about there. Oh, wait. So we get our regularity formula by just, again, subtracting off that codimension, which was already hanging around in our formula. So as we're sort of leading ourselves back towards this more general Kazhdan-Lusztig conversation, it's helpful to look at some of the underlying combinatorics that was guiding our rule. Because in, for example, the Pechenik-Spire-Wigand argument, in which they give formulas for all matrix Schubert varieties, their techniques were using these derivatives of growth unique polynomials by Himmelker, Pechenik, Wigand. Okay, so these techniques that we were using were rather different to theirs. Our formulas were more so in terms of the underlying combinatorics of these pipe dreams, which in the settings that we were talking about, we were able to reframe in terms of combinatorics of excited Young diagrams. And while the technique of using these derivatives does not necessarily, or does not straightforwardly extend to the more general Kazhdan-Lusztig setting, we will see that by looking at the combinatorics of excited Young diagrams, this combinatorics will nicely extend to some more cases of these Kazhdan-Lusztigs. So this is a case where different techniques allow us to generalize these results in different directions, which is fun. All right, so I've mentioned these excited Young diagrams, so what are they? You'll see these excited Young diagrams, for example, popping up in the equivariant cohomology of the Grassmannian, perhaps. I don't know if you talked about that at all in the first week. But here we will talk about sort of the K-theoretic version of this. And so for this, we'll start with some big partition mu, which I'll draw the Young diagram for, and a smaller partition lambda that will fit inside of this bigger partition mu, which I'll draw with pluses. So I'll draw the Ferris diagram of the smaller partition inside of mu. And what these excited moves are is I can sort of very similarly to these ladder moves here, except they're only the most simple ladder moves you can think. I can, if I have no pluses in these entries here in my subdiagram, I can either move a plus southwest, or similarly to our ladder moves, I can leave a copy, and that's giving us the K-theoretic excited Young diagram. If you want to do ordinary excited Young diagrams, you just forget about this leaving an extra copy option. Okay, so what we'll do is, starting with our initial configuration, which is going to be this Ferris diagram of lambda inside of this game board of mu, we'll apply all of the possible K-excited Young diagrams that we want. And so if we do any successive moves, that will give us all different K-excited Young diagrams. So here I have a few examples of different K-excited Young diagrams for lambda in mu, where this first one is our initial diagram, this second is doing only ordinary excited moves, and this one is doing one K-excited move here, and then this diagram isn't doing any K-excited moves. All right, so how does this pop up in terms of what we've been discussing? We can actually think about this vexillary Grothendieck polynomials precisely in terms of these K-excited Young diagrams. So you might be familiar that for every vexillary permutation, we can actually associate it with a pair of Grassmannian permutations, which you can read off by just looking at the Rotha diagram for that vexillary permutation, which we'll see an example of. But using this pair, mu lambda, we can write down all of the K-excited Young diagrams associated to that pair. And again, by recording the number of pluses in each row, just like we were doing with our pipe dreams, we can again read off a polynomial, which will again give us this vexillary Grothendieck. Okay, and so when we're talking about the degree of this Grothendieck, of course, just in the very same way, trying to compute the degree, or computing what is the highest weight monomial that we could have, this again amounts to doing the most of these K-excited moves that we can possibly do. And one thing that you can see popping up is exactly the structure of our theorem here. So when we're talking about trying to do the most possible K-excited moves, here I could try to just haphazardly move pluses. And here I'll get 3 extra pluses using these excited moves. But if I'm sort of trying to maximize my moves by having these moves emanating from boxes that are on a longest diagonal, that is essentially how I am maximizing the number of these K-excited moves. And this is exactly where this statistic of the maximal diagonal in our formula is coming from. And this statistic is what is going to generalize to more of these Kazhdan-Lusztigs. All right, so in terms of these Kazhdan-Lusztig varieties, we've answered the question for the Kazhdan-Lusztig varieties that are matrix Schubert varieties. And as it turns out, if we go to what is the most reasonable place to start for Kazhdan-Lusztig varieties, which might be well behaved, so a good place to start is Kazhdan-Lusztigs indexed by a pair of Grassmannian permutations. And let's see what we can do there. And as it turns out, these Kazhdan-Lusztigs that are indexed by this Grassmannian pairs are just isomorphic to vexillary matrix Schubert varieties. And so by this isomorphism, we know that their regularities will coincide, and we can again apply our formula. How you can see what this correspondence is from this Grassmannian pair to this vexillary permutation is almost precisely coming from this correspondence between Grassmannian permutations and partitions, and the correspondence between vexillary permutations and a pair of partitions that I was mentioning earlier. So this pair of Grassmannian permutations are corresponding to this pair of partitions here. If I do the maximal, the most possible ordinary excited moves that I can do, moving my pluses as southeast as possible, then I can just read off the Rotha diagram for this permutation B. And so we see for this Kazhdan-Lusztig, the regularity, since this is giving us this vexillary example that we saw earlier, the regularity is going to be 4 in this case. All right, and so what are some applications? So I said that these Kazhdan-Lusztigs can pop up all over the place, and one way that we can see them is through one-sided mixed ladder determinantal varieties. So these were introduced in the late 80s by Abhyankar precisely to study singularities of Grassmannian and Schubert varieties. So it shouldn't be necessarily a surprise that these varieties are actually going to be Grassmannian and Kazhdan-Lusztig varieties. But how they are defined is we'll start with a Young diagram that we'll fill with indeterminates Zij. And along this boundary of the partition, I can mark some of these purple points here where I'll assign labels, integer labels, that will tell me if I'm looking at the submatrix whose lower right corner is given by that marked point, that'll tell me to take that size minors for my defining ideal. This isn't working. Okay, so here this would tell me for this defining ideal, I would take the 1 minors there, so I'll have Z11, Z12, Z21, and Z22. And then this marked point, here we go. This marked point will tell me to take all of the 2 minors of this region. So that would contribute this 2 by 2 minor here. And I can continue and add that last 2 by 2 minor, although that last minor isn't going to quite matter. All right. So we have that these one-sided mixed ladder determinantal varieties are going to essentially by their definitions, we know that they should be isomorphic to these Kazhdan-Lusztig varieties indexed by this Grassmannian pair. And it's also been known for some time, for example, identified in the Knudsen-Miller-Young paper, that these one-sided mixed ladder determinantal varieties are also vexillary matrix Schubert varieties. So again, we can apply our formula for these anti-diagonals to compute the regularities of these one-sided mixed ladder determinantal varieties. Okay. And so as I mentioned, these varieties have been well studied, and specifically a related statistic on these one-sided ladder determinantal varieties has been studied for some time. This statistic is called the A invariant, which is closely related to the Castelnuovo-Mumford regularity. And this A invariant, the papers that exist to compute this A invariant combinatorially have been in terms of lattice paths on these ladders. And so I'm just going to show you what this connection is between these lattice path calculations and our excited Young diagrams. All right, so to these one-sided ladders, I can associate a family of non-intersecting lattice paths where the marked points here are going to allow me to read off starting points that I'll label on the horizontal boundaries of my ladder and endpoints that I'll record on the vertical boundaries of my ladder. And so it's a fairly straightforward algorithm to label these start and end points. And so what we do is look at all of the lattice paths that are non-intersecting, where I'm connecting my starting points to ending points. As it turns out, the k polynomials of these one-sided ladder determinantal varieties, of course, these are going to be our vexillary Grothendieck polynomials. And it's also been identified, for example, in Knudsen-Miller-Young, that these are determinantal expressions for these k polynomials. So I can write the vexillary Grothendieck polynomial as just a determinant of polynomials, similarly to how you can for flagged Schur polynomials. And so it shouldn't be necessarily a surprise that you can write the generating function so that you can realize the monomials as coming from lattice paths, sort of through a Lindstrom lemma sort of construction. Okay. And so as identified by Krodenholler and Gorpade in 2015, they were studying particular one-sided ladders where they put additional restrictions on where these sort of starting and ending points could be labeled. They found that a related invariant called the A invariant can be computed in terms of recording elbows, these particular elbows in these lattice paths. And what this has to do for regularity is the regularity is exactly going to be recorded by the number, precisely the number of elbows, the most number of elbows that you can have among these non-intersecting lattice paths. What this is coming from is these non-intersecting lattice paths are in straightforward bijection with excited Young diagrams. Because to each of these diagrams, in this blank space that I have here, I can fill all of those with pluses. And you can see that every time I'm sort of straightening out one of these kinks, so if I straighten this elbow to be an elbow like this, then that would correspond to doing one of these excited moves. So this shouldn't necessarily be surprising. But one thing that's nice is recording the number of elbows is exactly telling me that I can do this number of these k excited moves. Because it would tell me that I sort of have this position empty when I have a plus here. And so this is actually the same one-sided ladder that is corresponding to the vexillary permutation that we've been using throughout this talk. And you can actually see that the positions of the elbows in this lattice path, so this is a maximal one, the positions of elbows here are exactly the positions of these maximal number of pluses that I had on the previous slide. So again, these lattice paths are exactly telling us that we want to compute these longest anti-diagonals. All right, so I think we've maybe gotten as much as we can out of the Grassmannian formula. So let's push forward to see how much further we can generalize, because there are many more homogeneous Kazhdan-Lusztig varieties than just the Grassmannian case. And so to do this, we would certainly need a nice combinatorial formula for the k polynomial for these Kazhdan-Lusztig varieties. And in their 2012 paper, this is precisely provided by Wu Yang. And so this formula is given in terms of precisely these pipe dreams that we were talking about that were defining the Grothendieck polynomials, but we're just going to keep some of them. And the ones that we keep are going to be determined by this extra permutation V, or U. So this larger permutation is going to determine which of the pipe dreams I'm going to keep to contribute to my final unspecialized Grothendieck polynomial. So for this pair, UW here, this larger permutation W is going to give me a game board that I'm going to apply do all of these pipe dreams on top of. And this game board is just going to be what is the bottom pipe dream for this larger permutation. And so for this larger permutation U, the bottom pipe dream is just these two tiles here. So I've shaded them. And so what this rule says is I'm just going to keep all of the pipe dreams for the smaller permutation whose pluses are all supported in the shaded region. And if we write out all of those pipe dreams, the only one that's going to survive is this middle one, giving us that this unspecialized growth unique polynomial for this particular pair is just going to be the monomial x1. Right, so this is going to squash many of the monomials that would ordinarily appear. But if we're starting with a very large permutation here, so if I would have started with the permutation u being 3, 2, 1, for example, then I would get everything. And so that'll tell me that if I take u to be as large as possible, then I'll just get the ordinary growth unique back. And so in cases in which we have maybe some nicer combinatorics, we might be able to easily compute what the degrees are in this case. And the nicer combinatorics is going to precisely come from when this pair of permutations is, rather than Grassmannian, 3, 2, 1 avoiding. And this is coming from exactly the fact that if our permutation W is 3, 2, 1 avoiding, we're never going to have to do these more complicated ladder moves. They're all going to be simple, which is going to make the combinatorics much easier to track. And so this algorithm is, again, going to be in terms of excited Young diagrams, but they're going to be a bit different because we're no longer working on a partition. We're instead going to be working on a skew partition and doing excited Young diagrams there. The reason for this is you can naturally, one definition of 3, 2, 1 avoiding permutations, those are the ones that when you draw out the Rotha diagram, after you delete extra rows and columns and sort of glue together, you'll be left with a skew partition up to a reflection. All right, so for these k-skew excited Young diagrams, I'm going to start by taking my big permutation and doing exactly this operation that I said. So I'm going to take the Rotha diagram for the big permutation, delete the empty rows and columns, and glue together. And I'm going to define an initial configuration of pluses that I'll associate to this smaller permutation u. This is in terms of all of the underlying combinatorics is coming from the subword complex, so you can just accept that there is a unique initial configuration of these pluses u that we're getting, but this initial configuration is coming from the earliest subword of u in w, or of w in u, which I know must exist because w is less than or equal to u in Bruja order. So I know I can find one of these subwords. All right, so that'll give me an initial configuration of pluses here. So this is a particular initial configuration associated to this pair of permutations. And here I've drawn out all of the possible k-skew excited Young diagrams. So the local rule is exactly the same. So nothing different there. And so one nice thing is the combinatorics that's governing these unspecialized growth unique polynomials. So that was supported on what you're recording monomials from the pipe dreams of W that were supported on the bottom pipe dream of U. This is going to biject with these skew Young diagrams here. And so instead of computing here, we can instead compute everything on the level of these skew Young diagrams. And so in my current work, what I'm doing is I give an algorithm that will tell you, based on these skew Young diagrams, I can construct you what is going to be the maximal one. And so here I just give an example of this algorithm here, which I'm not going to give in great detail, but I'm just going to sort of sketch it so you can see the general flavor. So I'll start with the initial excited Young diagram here. And for the algorithm, I'm going to operate on each connected component of pluses, moving right to left. And so what I'll do is here I first am going to bold the lowest westmost or eastmost diagonal of pluses here. So here, the longest diagonal of pluses I have bolded. And once I've bolded, I'll shade sort of a highest choice that's sort of weakly above this diagonal here. So that second condition is a bit technical, but I'll bold and then I'll shade a diagonal that is the same length. That's going to be above what I've done. And then the second move, after I've done my shading, is any pluses in this component that are weakly below what I've shaded, I'm going to do as many moves as I can to expel those southeast. Okay, so here there's nothing southeast of this shaded bolded region, so I move on to the next connected component. These are the pluses. This is the longest diagonal that I can find, but according to some calculations that I do, I decide that this is the diagonal that I actually want to compute in terms of. I then expel all of the pluses that are south of this diagonal that I've identified. And then from each of these shaded pluses, I do as many of these k-excited moves that I can do. And I just keep track of how many that I did, where here I'm marking them with these purple boxes, which tells me that the regularity in this case is going to be 7. Okay, so this algorithm is in terms of we component by component identify a longest diagonal that's hopefully as high as possible, expel pluses, move on to the next component. And we keep doing this, and then do as many of these moves as we can. Okay. And what this is connecting to is a special case of these 3-2-1, 3-2-1 avoiding Kazhdan-Lusztig varieties are precisely two-sided mixed ladder determinantal varieties. So instead of taking minors of a region of indeterminates that's given to you by a Young diagram, I can instead take minors on a skew-Young diagram, where I'm defining the minors in the same way, so labeling these marked points and taking northwest minors. And I'm missing an author here. I need to have Alex Fink here as well. But as an upcoming theorem of Fink, Escobar, Ratchgott, and Wu will tell us, these two-sided mixed ladder determinantal varieties are isomorphic to 3-2-1, 3-2-1 avoiding Kazhdan-Lusztig varieties. There definitely are 3-2-1, 3-2-1 avoiding Kazhdan-Lusztig varieties that are not two-sided mixed ladder determinantal varieties. But what this tells us is our algorithm that will tell us the regularity for these 3-2-1 avoiding Kazhdan-Lusztigs will thereby give us a formula or give us an algorithm to compute the regularity for these two-sided ladders. And I will close by saying there is a sort of two-sided version to this lattice path story, where now your lattice paths are constrained by this sort of crunch region of this skew diagram. And so in current work, we generalize a result in the same paper of Kazhdan-Lusztig, where we again generalize these computations to give an algorithm for the Castelnuovo-Mumford regularity for these two-sided ladders for the special case when we are working in terms of lattice paths. And in this case, what we want to be computing is these number of sort of unforced elbows, where, let's see, this last elbow here in this corner is forced by this skewing here. So we wouldn't want to count this elbow anymore. And so for the statistic for the regularity here, this would be our ordinary regularity that we computed in the last slide for the one-sided version, where I no longer would want to count that elbow anymore. So the regularity would be 3 in this case. But I'll stop there.